Let us continue with our 27th lecture. Till now we have talked about difficult to control dynamics. In the second part of this course, we spent considerable time on looking at inverse response systems and how one would control inverse response systems. And we followed that up with control of time delay systems, talked about the difficulties in getting the controller in terms of getting a realizable controller. And then I showed how the direct synthesis approach could be used to design the controller, and while we implement the controller, we also see that you have to use the model during the implementation of the controller also. And I said as we go forward, you will see more and more of the use of model directly in controller implementation. Nonetheless, we saw how we could get reasonable performance with closed loop control when you have inverse response and time delay systems. Of course, the time delay systems also introduces other complications in terms of stability analysis, and I showed you a new way of doing stability analysis for time delay systems. Now we come to the the last part of this difficult dynamics that we are going to address in this course, and that is control for unstable systems. Till now, if you notice, we talk about processes which are basically stable, and the instability could arise when we actually put the process in a closed loop and try to get more and more performance out of the process. So we have looked at systems which are inherently stable and not complicated from a stability viewpoint, but we always looked at by closing the loop, is there something that can go wrong, and can the closed loop be unstable while the open loop or the process itself is stable. So in other words, till now we have looked at how much performance gain I can get from a stable process before I push the closed loop itself unstable. Okay, so that's a kind of question that we have asked. So in other words, we have always designed controllers for performance while making sure they do not go unstable. However, if the system itself is unstable, that is, the process transfer function itself has unstable poles, then before we even talk about the performance of the system, the real first question that we need to answer is whether I can actually make this unstable process go into a stable closed loop. Okay, so that's a question that we have never answered till now. So this is the first time we are going to start answering the question. So the main question is, if the process is unstable, can you still come up with controllers which will make the closed loop stable? So we will start again to explain this idea with a very simple first order unstable process. So I have here a transfer function k over tau s minus 1. Typically we have looked at g is k over tau s plus 1, in which case s equal to minus 1 over tau is a stable pole. However, if I have k over tau s minus 1, then s equal to 1 over tau becomes a unstable pole, because this is a pole in the RHP. Now let us see what happens if I don't take this into account at all, and then say I am going to have a G desired, which is basically a stable G desired. Remember, the closed loop GMC by 1 plus GMC, the closed loop transfer function is what we are calling as G desired. So now what I am going to do is I am going to see if I actually choose a G desired, which is this. That basically means I am saying there exists a controller. I have assumed that there exists a controller which can satisfy this relationship, and once I satisfy this relationship, I know though the model itself is unstable, because this is a closed loop transfer function, the closed loop is stable because I have chosen a stable transfer function here. So the assumption is there exists a controller, and of course we have solved this, and then we have said the controller is basically 1 over gm times g desired by 1 minus g desired. So let us see what type of controller we get. So if I substitute this 1 over gm here and g desired divided by 1 minus g desired, I get this form here, and you will quickly notice that this is going to be, you can write this as tau over k tau c 1 minus 1 over tau s. So this, you can write this like this, and now you will notice that this is your PI controller with a gain of tau over k tau c, and you are going to have a time constant which is going to be minus 1 over tau. So, not time constant, so sorry, the integral parameter in the PI controller is going to be minus 1 over tau. So, this is going to have a negative tau I. So, now I look at this controller and then say, well, this is a PI controller which is implementable, and I have an unstable process, and I have got the G desired, which basically is stable. So, it seems like I can always get a controller that will stabilize this first order unstable process and give me a closed loop response which is stable. Okay. So, then we can ask this question as to what is the problem with this, right. And when we look at this controller again, the only thing that seems different is that now I have a tau I for a PI controller which is negative. Other than that, there does not seem to be anything that is wrong. Okay. The thing that you also want to notice here is when we do this closed loop, one thing I just want to point out, when we do this closed loop which is GC by 1 plus GC, now G is K over tau S minus 1, C we have computed as tau S minus 1 divided by K tau CS divided by 1 plus G is again K over tau S minus 1, I have tau S minus 1 over K tau CS. So, when I do this closed loop computation, of course, this is going to turn out to be 1 over tau CS plus 1 because this is how we have actually designed the controller, but nonetheless I just want you to notice something. What we are going to do is we are going to do this pole 0 cancellations in the closed loop transfer function computation. Okay. So, this is something, if you notice, we have never done before in the closed loop computation. We did do pole 0 cancellation in the controller computation before when we talked about inverse response systems and so on, but we have never done a pole 0 cancellation during the closed loop transfer function computation. So, that is another difference. So, the two differences that I want you to notice are, one is the first time we are getting a negative tau I for the I part of the PI controller, and then we are also doing a pole 0 cancellation in the closed loop, which closed loop transfer function computation, which we have not done before. So, we want to see, because of this, are there any issues that come about when we do this controller design for unstable processes. Now, you will see something interesting. Supposing, let us assume for a moment that we designed a controller which was based on GM equal to K over tau S minus 1. Let us assume that the actual process, okay, G is slightly different from this, the K is the same, but let us say I have a time constant which is very slightly different, or slightly different from tau, which is tau prime. And then remember, when we talked about this before, I said you can design a controller based on GM, and that is your notion of the process, and you can actually say, okay, the closed loop behavior will be G desired if G is GM. But to really see the impact of a process which is slightly different from the model that you have chosen, what you should do is you should recompute GC by 1 plus GC using the actual model that you think is going to be operating. So, basically what we are saying is, while G desired is GMC by 1 plus GMC, to see the real effect of plant model mismatch when we want to compute the true closed loop transfer function, you should kind of put G process C by 1 plus G process C. And when this G process is slightly different from GM, we want to see what happens. Of course, when GP is GM, GCL will be G desired. So, this is something that we have talked about several times before. So, when we do that, I take this G is K over tau prime S minus 1, and let us just compute 1 plus GC and see what happens. So, when I do 1 plus GC, I have 1 plus K over tau prime S minus 1. The controller still remains to be the same because the controller was built based on the model, which is tau S minus 1 divided by K tau CS. Okay. Now, notice in the previous case, because tau prime and tau were the same, we cancel this in the closed loop transfer function, we got our pole 0 cancellation. But now we have assumed that this tau prime is slightly different from tau, so we cannot do this cancellation. So, I will get this tau CS tau prime S minus 1 plus tau S minus 1 and divided by this, and then you will have another GC. But remember, the stability of the system really depends on the zeros of this 1 plus GC, which is what we saw again in the last lecture on Nyquist stability. So, we look at this polynomial and then say the poles of GC by 1 plus GC are going to be the roots of this polynomial, which is the zeros of the numerator of 1 plus GC. So, we will expand this and see what happens. So, when I expand that, then I get tau c tau prime s squared plus s into tau minus tau c minus 1 is what I get. Now, this is a positive number. This will also be a positive number because tau and tau c are in my hand, because tau is the model tau. So, as long as I choose a tau c which is smaller than tau, which is what anyway I would want, because the closed loop has to be faster. So, the closed loop time constant has to be smaller than tau. So, this will also be positive, but whatever I do, I cannot get rid of this negative number. So, this will be negative. And if you go back to the root table that we talked about, remember the first step when you do this polynomial is, once you make the leading coefficient of the polynomial positive, then the first level of check we do so that there is no pole in RHP is to check for if every coefficient is positive. Now, this is positive, but this is negative and I can do nothing about this. So, this will have roots in the RHP. So, this is something that you cannot get rid of. Now, so what that basically says is that even if you have a small difference between tau and tau prime, okay, this cancellation does not work anymore, and because this cancellation does not work anymore, I land up with unstable poles in the closed loop transfer function. So, even if there is a minor change between the true process and the model that is used, then the controller becomes unstable. So, this is not at all a robust controller. So, this controller will work and will work well only when the process and model are exactly the same, which is very unlikely to occur. So, this is not a controller that can be implemented to stabilize the behavior. And we notice that this really happens because we have this pole 0 cancellation not happening in the controller equation, but actually this pole 0 cancellation in the nominal case where the process and model are the same is happening in the closed loop transfer function computation. So, as a general rule, pole 0 cancellations in the closed loop transfer function computations can lead to robustness problems. So, that is something that we should be wary of and avoid it as much as possible. So, now that we have this, we are back to the question of how do I solve this problem, right? Because it looks like if I use this direct synthesis approach, I get a G desired, and I get a G desired which is basically going to tell me to keep a 0 where the unstable pole for the model is, and then that will essentially come into a pole 0 cancellation situation in the closed loop. Okay. So, one idea is to see whether we can avoid this pole 0 cancellation and make the controller robust also. And again, this is the beauty of this whole idea. So, basically what it says is, okay, there are two places where I can do the pole 0 cancellation. I do not want to do this in the closed loop transfer function computation. So, maybe I should do this pole 0 cancellation in the controller computation, right. But if I want to do this pole 0 cancellation in the controller computation, if I give a standard G desired which is 1 over tau Cs plus 1, then there is no possibility of a pole 0 cancellation in the controller computation. So, basically what that does is it forces me to choose a G desired which is not my preferred 1 over tau Cs plus 1, but something else. So, basically I am constrained to change my G desired because of the unstable pole. So, this is where if you have an unstable process, again that limits your performance, just like how inverse response limited your performance, just like how time delay limited your performance. Unstable processes also limit your performance because you are not free to choose any G desired you want, because if you choose any G desired you want, then that will leave a pole 0 cancellation in the closed loop computation, which is, as we showed here, is a problem in terms of the stability of the closed loop. So, we will see whether we can modify this G desired so that we induce a pole 0 cancellation in the controller computation. So, that is the basic idea. So, the standard technique to do this would be instead of saying I will have just 1 over tau Cs plus 1, what I am going to do is I am going to add another tau Cs plus 1 term here, another tau Cs plus 1 type of term here. Then I have a new G desired, which is tau Cs, so tau C1s plus 1 divided by tau C2s plus 1 times tau C3s plus 1. So, the motivation is, so I have this 1 over let us say tau Cs plus 1 term here. I want to go away from this so that I can get a pole 0 cancellation. At the same time, I do not want to go very far away from this also, because this is a G desired that I like the most. So, it is like this. So, I am going to multiply and divide this by a similar term, which is tau C1 tau C. In this case, if you assume this is tau C2, just so that I show you the same thing there. So, supposing this was your most desired situation, now you are not able to get this because the pole 0 cancellation occurs in the closed loop. So, I want to have something very close to this, but at the same time where I have the possibility of inducing this pole 0 cancellation in the controller computation. So, what I am going to do is I am going to add one term here and one term tau C3s plus 1. Now, if you notice, if I keep tau C1 and tau C3 very close to each other, then this and this will be very close to each other, and basically you go away from this tau C plus 1 s plus 1 form, but by not by much, and I can control how much I go away from this form by choosing this tau C1 and tau C3. So, if they are chosen close to each other, then this numerator and denominator are very close to each other. So, in terms of going away from a desired transfer function, you are not going very far away. However, now I will show you by doing this modification how we can actually induce a pole 0 cancellation in the controller transfer function. So, we start with this G desired, which is tau C1s plus 1 divided by tau C2s plus 1 times tau C3s plus 1. And then simply go through the algebra. So, this step is just putting this back in, and in this step what we are doing is we are taking this to this side and then simplifying it, and then when you further simplify it, you will get this form right here. So, this is a form that that I want you to look at. So, basically you can do this computation at home. This is very simple algebra. So, once you do this algebra, this controller is tau C1s plus 1 divided by Ks tau C1 minus tau C2 minus tau C3 divided by tau s minus 1, and inside the bracket I have tau C2 tau C3 divided by tau C1 minus tau C2 minus tau C3s minus 1. Now, you notice that my interest is in introducing a pole 0 cancellation in the controller transfer function. So, to do that, somehow I have to cancel this term and this term, and now notice this tau, this k over tau s minus 1 is a model. So, the tau is what I have chosen as one of the model parameters to represent the process. Tau C1, tau C2, tau C3 are all choices that I have made for my G desired. So, I can choose them to be whatever I want. So, if I choose this to be equal to tau, then I will have tau s minus 1, and in the numerator I will have tau s minus 1. So, I can do this tau s minus 1 tau s minus 1 cancellation. So, notice how I introduce a pole 0 cancellation in the controller computation. So, if I set tau C2 tau C3 divided by tau C1 minus tau C2 minus tau C3 is tau, then I can cancel this tau s minus 1 and this tau s minus 1, and what I will be left with for the controller will be tau C1s plus 1 divided by k times tau C1 minus tau C2 minus tau C3s. Okay, now just for convenience, if I just write this as tau C1 minus tau C2 minus tau C3 is tau C, a new definition of a variable, then the controller will become tau C1s divided by k plus 1 divided by k tau Cs. Okay, and this you will again quickly recognize this is the PI controller, and the PI controller. So, this again, this is the same trick that we have been using for a while now. So, this can be written as tau C1 divided by k tau C into 1 plus 1 by tau C1s. Okay. So, this tau C1 by k tau C is the gain of the PI controller, and this is the integral time constant of the PI controller. So, what happens now is remarkably when we temper our expectations for G desired, by going away from what we would like to have, which is this form of 1 over tau Cs plus 1, by adding a pole and a 0 to the G desired, and then as I said before, you can control how far away from this G desired you are going by manipulating this tau C1 and tau C3 values. But basically we introduce this, and then once we introduce this and put this into the controller computation, then we get another choice where I can set this tau C2 tau C3 divided by tau C1 minus tau C2 minus tau C3 is tau, which induces a pole 0 cancellation in the controller computation, which leads to a PI controller for an unstable system. So this is a very interesting idea now, right. So see the difference between this and the previous case. In the previous case there is no pole 0 cancellation in the controller computation. Now that we have done this, now for all this effort that we have taken in doing this, we want to know whether we get any purchase out of this. What that basically means is that because of doing this, has my controller become robust, is the question that we are going to ask. And to answer that question, we take a process which is different from the model that we have used, which is k over tau prime s minus 1, the same thing that we did in the previous analysis that I showed you. Now I do 1 plus GC, I have 1 plus k over tau prime s minus 1, and now this becomes the controller. This controller in the previous case had a 0 in the right half plane, which was tau s minus 1. Because I have cancelled this out, this controller is a simple PI controller that I have here. And now if you do the manipulation and do this, you will get a closed loop transfer function which is of this form, which is given here after all the manipulation is done. So you can follow through these equations and then basically derive this closed loop transfer function. Now when you derive this closed loop transfer function, you notice now the denominator is where I have this as a positive number, because tau prime is the true process time constant, and that basically is a positive number the way we have defined this. Tau c is my choice and I choose that to be positive. Tau c1, tau c2 also my choice, so this is also positive, this is also a positive number, and you can show that this is going to lead to a stable closed loop. Okay. So by introducing the pole 0 cancellation in the controller computation, even though the process is different from the model that is used for the calculation of the controller, we show that the closed loop will still be stable, which is very different from what we had before. And also look at how beautiful it is in terms of a final result actually being a PI controller, even for an unstable process. The only thing is the PI controller is designed in such a way that the G desired, if the process and model are the same, is not going to be a very simple 1 over tau Cs plus 1, but on top of it there is a 0 and pole that have been added. So in some sense we have gotten a robust controller by giving up on the performance that we expect. Now let us do some kind of sanity checks on all of this. So the kind of things that I am going to do is that if this tau prime is actually equal to tau, then I am going to see whether I'll just to make sure that I have not made any mistakes here. I just want to show you how you can do some of the sanity checks. So you would expect if tau prime is equal to tau, then you would expect to get the G desired that we actually use to compute the C. That is one thing that we can look at, and then we can also look at whether I can do some tricks to still get whatever I want, and I will show you why all of that will create problems and so on in the next slide. Okay. So if you look at this, the G desired is the following. With the definition tau is tau c2 tau c3 divided by tau c1 minus tau c2 minus tau c3, and this is tau c, and gc by 1 plus gc, assuming the process is slightly different from the model, is this equation. Now just for curiosity, if you put that there is no planned model mismatch and then you say tau is tau prime, then you will see that tau is tau c2 tau c3. Okay, so you know tau is tau c2 tau c3 by tau c, because this is the definition here. So if tau prime is tau, then if you take the denominator of this, tau prime is tau. So, tau prime is going to be tau C2 tau C3 by tau C times tau C S squared plus S into tau C2 plus tau C3 plus 1. So, this and this will get cancelled. Now, you can write this as tau C2 S plus 1 times tau C3 S plus 1. So, which is what will go here. So, which will what be your G desired. So, if this tau prime is exactly tau, then we get the G desired that we started working with, right. Now, if tau prime is different from tau, then you actually do not get this G desired, you get something slightly different from this G desired. So, everything seems to work out here nicely. Now, if you said, oh well, now that I have this and I seem to have a stable controller, maybe now I go back and think about this a little and then say, well, if I want my G desired to be of the form 1 over tau C S plus 1, maybe what I can actually do is, now that I have done this, what will happen if I actually set tau C1 equal to tau C3, okay. So, if that happens, I will cancel this and this, and then it looks like everything is great, right, because I get my transfer function form, which is of the form 1 over tau C2 S plus 1, which is the best possible that I have been wanting, and still the closed loop is all okay and so on. So, you will quickly notice, if you do this, tau C1 is tau C3, then you will notice that tau C will become minus tau C2, okay, and once you have tau C is minus tau C2, then you will have a negative coefficient here, which will make your system not robust if tau prime is not equal to tau. So, if tau prime is not equal to tau, you have to retain this term as the same term. Now, if I set tau C1 equal to tau C3 to make sure that I get only a form of 1 over tau C S plus 1, then from this equation tau C1 and tau C3 will get cancelled. Now, tau C will become minus tau C2, then you will have minus tau C2 tau prime S squared plus S into tau C2 plus tau C3 plus 1. This could be a positive number, this could be a positive number, but I basically have a problem here because I get a negative number here, which will again lead to unstable behavior. So, this beautifully illustrates that while you have this G desired, as long as these two are not the same terms, the system will be stable even when you have process model mismatch. But the minute you make these two terms the same, if I had a process model mismatch, immediately I will get a negative here, okay. So, even a slight process model mismatch will lead to problems, okay. So, it seems to make sense in terms of all of these ideas coming together in this example of controller design for unstable systems, okay. So, at this point we can kind of summarize the three different things that we have learned in controlling difficult to control systems. So, we started with inverse response. I described inverse response as systems where the initial direction of change is different from the final value, and I gave you examples and showed you why these are difficult systems to control. And the problem while inverting the model, which is where this is a problem while inverting the model, is basically related to the controller, because the controller is 1 over Gm G desired by 1 minus G desired, right. So, the inversion comes in the controller computation. So, if I have inverse dynamics, then I have unstable controller. So, the solution to this we saw was to introduce inverse response in the desired G dynamics itself, that is, include a inverse response term for G desired. Then what happens is I have a pole 0 cancellation in the controller computation, and the comment is we are forced to introduce this inverse response in the desired dynamics. So, basically the maximum achievable performance that we can get out of these systems become limited. The other comment is the pole 0 cancellation in the controller calculation does not lead to robustness issues. We showed that even if the 0 of the model process transfer function is quite different from the model, we still do not see robustness problems in the particular example that I showed you. So, this is as far as inverse response is concerned. Then we went to time delay. and if you use whatever G desired you want with the time delay system, then I showed you that you will get an unrealizable controller, which basically meant that if you wanted to find the UT from the controller, then it would require error at t plus tau d, that is future errors that it would require, which is not feasible. So, you will end up with an unrealizable controller. So, the solution is to temper our expectations for G desired by actually introducing time delay in the G desired dynamics, in which case again the maximum achievable performance is limited, because you have to really have things happen with the delay, and it just says there is no way of getting around it. The other comment here is that the stability study requires newer ideas, and that is where we came up with this Nyquist plot for understanding the stability of the systems, and which involves quite a bit of complex mathematics, but basically we finally reduced it to simply looking at some plots to understand what happens. The last difficult dynamics we talked about was unstable systems or unstable pole. We talked about system with one unstable pole. You can expand this to have more unstable poles, and how you describe those and so on. And while you inverted this, it did not seem like a problem, it just looked like you got a negative tau I for a PI controller, but other than that just the first loop did not seem to have any problems. But I showed in the closed loop, if the process is even slightly different from the model, then you get controllers which are not at all robust. It means if the process is slightly different from the model, you get an unstable controller. So, learning from here, where we said this pole 0 cancellation in controller does not lead to robustness problems, whereas here we saw this robustness problem came because I am doing pole 0 cancellation in the closed loop transfer function computation. So, learning from here, we said let us move the pole 0 cancellation from the closed loop computation to the controller computation. So, we introduce pole 0 cancellation in the controller computation, and this basically means that I cannot use any G desired. This is where the performance limitation comes. I have to temper my G desired with more terms, which I did, and then we saw that we got a PI controller, and in the closed loop, even with process model mismatch, we saw that we can get a robust controller, which was not possible without this. So, interestingly, all of these are nice interrelated ideas, borrow one idea from one system to another and so on, and it is also a very nice way of thinking about control. And if you do not have very difficult dynamics in your process, most of controller design is very simple and controllers operate quite well, and only and of course you can ask for any performance you want, and to a large extent you will be able to achieve that performance. And the controller design and thinking about controllers become complicated only when you have complicating dynamics. And in terms of complicating dynamics, we showed you 3 different types of dynamics, and if you were not doing this using the direct synthesis approach, you are just let us say doing the stability based tuning, it would be very difficult to understand where the performance limitation comes from for these difficult dynamics, right. You will still do some find the gain at which the system becomes unstable, and then you will back off and so on. In that way of doing, you have no notion of how much you are backing off and how much you are backing off because of difficult dynamics and so on. So, those notions all get clubbed into this backing off idea. However, when you do this direct synthesis approach for controller design and start understanding this, then if you say my gold standard is G desired, and if there is a process which allows me to choose G desired any which way I want, then I would say that process is not limiting me in any sense. It is not the actual G desired itself, but the choice of G desired should be completely up to me, in which case the process does not limit me from choosing any G desired. So, I would say there is no performance loss. However, if I have to add certain things to my G desired because of the dynamics, then we say that I have some performance limitations that are introduced because of this difficult dynamics. In the inverse response case, I am forced to add an inverse response in my G desired. In the time delay case, I am forced to add a time delay in my G desired, and in the unstable process case I am forced to add extra poles and zeros in my G desired. So, there are certain constraints that are placed on G desired and I have to adhere to those constraints, and that is where the performance limitation comes from. So, hopefully this simple idea of direct synthesis leading to these kinds of insights for difficult dynamics is clear and interesting to people taking this course. Thank you, and I will see you in the next lecture.